Hello everyone. Today we are covering our fourth section called Manipulating Data and Types of Distribution of our Data and Statistics unit. To begin, we have this data set here and their scores from a recent quiz, and we are going to take that data and we're going to find the median, the mean, the range, the interquartile range, and the standard deviation. Once we have found our numerical measures for the original data, we're going to see what happens if we are to adjust all data points in the set by adding 4 to them. We're going to see what happens when we multiply each part of our data set by 3, and then we're going to see what happens when we multiply by 3 and add 2. So all of this calculating is going to be done on the calculator, and we're going to switch to a video that covers all of the calculator steps in just a moment, and then we'll come back from that video and we will have all of our data in our chart. So if you go ahead and click Stat, I'm not going to show you how to add your original data in, as we've already done that. So all my data is in list 1. I'm going to click the right arrow and I'm going to go over to L2. I need to be up in this top bar, so I'm going to hit the top arrow, the up arrow. And now my L2 is highlighted. So in list 2, I want my data to all increase by 4. So to change all of the data in L1, I'm going to hit second, and then I'm going to come down here, and the 1 key has this little blue L1 right above it. And when I hit that, that says that I'm working with list 1. And I want all data sets to be increased by 4, so I'm going to hit +4, and then I'm going to hit enter. And that calculates 95 plus 4, 90 plus 4, 95 plus 4 for the entire list. Now, we not only are calculating our data +4, but we also are calculating our original data times 3. So I can do that in my next list. So I'm going to hit my right arrow key. Now I'm in list 3. I'm going to go up. Now L3 is highlighted, and I want my entire first list to be multiplied by 3. So I'm going to again hit second. I'm going to choose L1 times, oh, that was the division. So I'm going to go back and hit delete, times 3 and hit enter. And now my first list has all been multiplied by 3. 95 times 3 is 285. 90 times 3 is 270, and so on. Now I'm going to arrow over, and I'm going to do both of those things at once. So now I'm in list 4. I'm going to go up. I've now selected list 4. In that, I am multiplying by 3 and adding 2, but I need to make sure that I'm using parentheses so that I'm getting the multiplication before the addition. And your calculator can do order of operations for you for the most part as well, but we're going to put parentheses just in case. So I have parenthesis second, option 1, because again we want list 1, times 3, close the parentheses, and then we are also adding 2, hit enter. And now we have list 1 times 3 plus 2 for each data point. Now when I'm calculating my numerical values, I'm going to again hit stat. I'm going to arrow over to calc just like we did before. I'm going to select one variable statistics, 1 bar stats, hit enter. Now's where this changes. So previously all of our data was in list 1, so I wanted my list to say L1. Now my data is in different lists, so I need to change the list that we're in using these little blue numbers that are above the keys. So I have L1 above 1, L2 above 2, L3 above 3, L4 above 4, L5 above 5, and L6 above 6. We only used lists 1, 2, 3, and 4. List 1, we had our original data, so if I were to calculate that as is, that's our original data. There's our mean from our original data. If we want the measures from when we added 4 to each of those things, we have to go back over to calc, select that, and we're going to change this to be L2 because that's where our data is. And notice that this flashing cursor up here already has an A in it. That means that alpha is selected. If I want to select list 2, I need to change again to second. So I'm going to hit second, and that's L2. Now it's going to calculate for my second list, where my data was all increased by 4. So my mean is now 77.93, and my median down here is now 91.5. My range, 104 minus 4 is 100. My interquartile range, 94 minus 79 is 15. And my standard deviation, again, we're using SX, so we're looking at 31.7. You do the same thing for each of those other lists. So you'd go Stat, go over to Calc, select 1. If you want the data where we multiplied by 3, you're going to hit second, list 3, and go down and calculate. If you want list 4, where we multiplied and added, you're going to hit Stat, go over to Calc, select option 1, change this to list 4, and hit calculate, and there is all of your data. Okay, now that we've used our calculator to find the median, mean, range, interquartile range, and standard deviation for all 4 data sets here, I'm going to run through what each of these points are. So for the original data, you should have gotten a median of 87.5, a mean of 73.93, a range of 100, an interquartile range of 15, and a standard deviation of 31.72. For the second data set, when we added 4 to each of those things, you should have 91.5 for your median, 77.93 for the mean, 100 for your range, 15 for the IQR, and 31.72 for your standard deviation. Then for multiplying everything by 3, you should have 262.5 for your median, your mean should be 221.79, your range should be 300, your IQR should be 45, your standard deviation should be 95.16. For the fourth data set, you should have 264.5 for your median, 223.79 for your mean, 300 for your range, 45 for your IQR, and 95.16 for your standard deviation. So now that we have all of that data in our tables here, we're going to take a look at what changes between our data sets. So starting with our original data to when we added 4, if you notice, the range is the same, the IQR is the same, and the standard deviation is the same. But the mean and the median both change. And if we're looking at this closely, 87.5 to 91.5, what's that difference? It's 4. What about the mean? 73.93 to 77.93. Well, 3 plus 4 is 7. 77.93 is 4 more than 73.93, which matches what we did to each number in our data set. So when we add 4 to each number in our data set, then the median and the mean both increase by 4. So I'm going to highlight median and mean, and then I'm going to write above it that we got this by adding 4. So from the original data, or the median and the mean from the original data, you take that number and you add 4. So if you're adding to your data set, then your median and your mean both increase by that same value, but your range, your IQR, and your standard deviation stay the same. But what about when you're multiplying? Let's go ahead and switch to a pink color for multiplication for our highlighting. And if we look at our original data to when we're multiplying by 3, our median again changes, our mean changes, the range changed, the IQR changed, and the standard deviation also changed. And I think a really easy way to tell what that change was is when we look at the range. We had 100 and now we have 300. So the range multiplied by 3, just like each piece of the data set did. And 15 times 3 is 45, 31.72 times 3 is 95.16, 73.93 times 3 is 221.79, and 87.5 times 3 is 262.5. So each of these pieces, median, mean, range, IQR, and standard deviation, all increased with the data set by 3. So to find those pieces, you take the values from the original data set and you multiply them by 3. So it's the original data times 3, or those values from the original data to be specific. All right, so we added and changed median and the mean. We multiplied and changed all of the pieces. But what happens when you multiply and then add? So if we look at our last data set here, we have times 3, and then to get from that median to this median, we add 2. And to get from this mean to this mean, from just multiplying by 3 to multiplying 3 and adding 2, you add 2. Or from the original data, 87.5 times 3 plus 2. From the original data, 73.93 times 3 plus 2 gives you your new mean. So when we are working with both multiplication and addition, the median and the mean change by both pieces. So you take the original data, so it's the original data times 3 and plus 2. And notice the multiplication piece is happening first. And that's what happened first in our data. It follows the order of operations. So you're multiplying first, then you're adding. But what about the range, IQR, and standard deviation? Did that change when we were using addition? It didn't. So between just multiplying by 3 and multiplying by 3 and adding 2, these pieces stay the same. So we're going to go back to that other color here, and we are going to highlight range, IQR, and standard deviation. And those things are only affected by taking the original data and and multiplying by 3. The addition has no effect. All right, so let's summarize each of those things. For a new value, new data set, and you're taking that data set and you're adding A to it and you're multiplying it by B. That's what's happening right here. So we have X new is equal to A plus B times X, where X is every piece of your data set. So for our median, it is affected by both multiplication and addition. So you take the original median and you multiply it by B, and then you're going to add A. If you didn't have any multiplication, you would only add. If you only had multiplication, you would only multiply. For the mean, you take the original value and you multiply it by the change in multiplication, and then you would add the change in addition. And both of those pieces, again, just like before, if you don't have multiplication, you just add. If you don't have addition, you just multiply. For the standard deviation, it is a little bit different. We have standard deviation from the original value multiplied by the change only, because standard deviation is not affected by addition. So our general term here is if you're multiplying, you multiply everything. If you're adding, it only changes the median and the mean. All right, let's go ahead and take a look at some examples. Starting with example 1, it says a teacher finishes grading quizzes. The class average is 84% and the standard deviation is 5.6%. However, the teacher is feeling extra generous and decides to give everyone 3% extra credit. What are the new average and standard deviation? Okay, well, let's start with recording our original pieces. So I have the average, the mean is equal to 84%, and I have the standard deviation is equal to 5.6%. And now it says that we are adding 3% extra credit. Does addition affect the standard deviation? It doesn't. It only affects the mean in this scenario. So we are going to go ahead and take our original mean of 84 and we're going to add that change of 3% to it. So that gives me 84 plus 3 is 87. So my new mean, x bar new, I'll zoom in here so you can see better what I'm writing. Our new mean is equal to 87%. What about our new standard deviation? Well, it didn't change, so it's still the same of 5.6%. And that is my answer, my new mean and my new standard deviation. All right, let's take a look at example 2. Suppose the average height of a class of students is 65 inches with a standard deviation of 3 inches. If we were to convert this to centimeters, multiplying by 2.54, what would be the new mean and standard deviation? Okay, so let's again record our original data. So I have my average height of 65 inches, so my mean is 65 inches. And my standard deviation is 3 inches. So I have S of x is equal to 3 inches. It says that we're converting to centimeters, so we're multiplying every inch by 2.54, so it'll be 65 times 2.54. Does multiplication change the mean, and does it change the standard deviation? It actually changes both. Remember, multiplication changes all of those pieces, the mean, the median, the range, the interquartile range, and the standard deviation. So I have two pieces of work to do here. So I have 65 times my change, which is 2.54, which is equal to 165.1 centimeters. And then I have to do my standard deviation as well, which was 3. 3 times 2.54 is equal to 7.62 centimeters. So my new mean, so x bar new, is equal to 165.1 centimeters, and my new standard deviation is equal to 7.62 centimeters, because once again, both of those things are affected by multiplication. And now I'll take a look at example 3. And example 3 does have something a little tricky that you have to notice first. It says, suppose the mean weight of a class of students is 184 pounds with a standard deviation of 21 pounds. The teacher wishes to convert this to kilograms. In other words, you're multiplying by 0.45. Furthermore, it was found that the scale was calibrated wrong and overestimated each student's weight by 10 pounds. What is the new mean and standard deviation in kilograms of this class's weights? Here's the thing. It says that they were overestimated by 10 pounds. So that means that before we can convert, we need to adjust for that 10 pounds. So this situation is saying that our subtraction of 10 pounds actually comes first. So it would kind of be written, if we were to write this as a formula, then you would kind of get something like the original mean, or the new mean, is equal to, in parentheses, the original mean minus 10, and then multiplying by 0.45. That's really what we're doing. That is the formula for what's going to happen here. And I'll leave that there for now. We're going to go ahead and record our data. So I have my original mean is 184 pounds, and my original standard deviation was 21 pounds. Before we do our multiplication, we're going to start with our addition or our subtraction. We're adding negative 10 or subtracting 10. Does the standard deviation get affected from a change in addition? And it doesn't. So even though we calibrated the scale wrong, it only changes the mean, it doesn't change the standard deviation. So I have my 184 minus 10, which is equal to 174. And now I can take that and I can change using multiplication. So I have 174 times 0.45, and that is equal to 78.3. And then I also have to do my standard deviation, so I have 21 times 0.45, which is equal to 9.45. So my new mean is equal to 78.3 kilograms, and my new standard deviation is 9.45 kilograms. And there is my answer. Example 4 says a certain data set has a mean of 19 and a standard deviation of 3.2. If every observation in the data set was multiplied by 3 and added to 5, what would be the new mean and standard deviation? Okay, in this question, it's specifying that you're multiplying by 3 and then you're adding by 5. So our multiplication is happening first. So let's again record our original data here. So I have my original mean of 19 and my original standard deviation of 3.2. So starting with multiplication, because that comes first in our instructions, I have 19 times 3, which is equal to 57. And the multiplication for standard deviation, I have 3.2 times 3, which is equal to 9.6. Now we have to work on our addition. Our standard deviation is again not affected by addition, so that just stays the same for the moment, but our mean does change, so I take that 57 and I'm going to add that change of 5, which gives me 62. So that means that my new mean is 62 and my new standard deviation is 9.6. And those are my answers. So now that we've looked at a few examples of calculating for a new mean and standard deviation when you're changing a data set, we also need to take a look at how data is distributed. So let's go ahead and turn the page, and we are going to look at the different types of data distribution. Starting with the normal distribution, a normal distribution looks like this. We call this a bell curve. It looks like a hill, and we describe this as being symmetric, so it is going to be equal on both sides of the hill. Symmetric. And most of the data clusters around the center. And then it tapers off on the ends. So what I'm getting at here is that since most of our data is around the center, that is within the main part of the hill, and then it tapers as you get towards the bottom of the hill on both sides. And again, with most of our data being centered around the middle, then if we are including, as it says in the instructions, the median and the mean, both of those things actually go right down the middle of our data set. So this is the mean and the median. So the median and the mean in a normal distribution are equal, and they're right in the center of our data. This is ideal. This is what we want our data to look like, but this isn't necessarily what our data always looks like, as you should know from the means and medians that we've been calculating for the past few days. They haven't been the same. But in a normal distribution and an ideal distribution, they will be the same and they'll be exactly in the middle. So next we have the symmetric distribution. And the symmetric distribution means that it is even on both sides of our data. So as some descriptors, values occur at regular frequencies and the mean, median, and mode are all equal and would be right in the center column. So it is equal on both sides. You have a steady increase on the way up and that exact same decrease on the way down. And this is the mean, which is equal to the median, which is equal to the mode. So all of those three things, mean, median, and mode, are all in this column. And just to clarify, when I'm saying that it occurs at regular frequencies, you're going up by 1, and you go down by 1. All right, next we have uniform. Uniform data is put in a graph that looks like this. So we start low, and then all of a sudden we jump up, and we stay up there for a while, and then we jump back down, and we end at the same level that we started at. And this is often considered rectangular, so I'm going to write that under the word uniform here. So it's kind of like AKA, it is a rectangular distribution. And to describe it, we're going to say that all outcomes are equally likely. So all outcomes are equally likely. And there's actually a formula for the mean in this situation, which is that the mean is equal to 1/2 A plus B. So your mean is going to be the average of A and B here. So to specify a little further, A is where your minimum will be and B is where your maximum will be. And then if we draw a line right through the middle, so we're averaging those 2 points, that's where your mean is going to be, which is that formula. And not only is the mean there, but it's also the median. So this is the mean and the median. All right, so now we've covered normal or a bell curve. We've covered symmetric distribution, uniform distribution. There's 2 left. We have these 2 pieces, something called skewed left and skewed right. So starting with skewed left, we have that the tail is longer on the left. So when you're thinking skewed left, you shouldn't really be thinking about where most of the data is. You should be thinking about where it's reaching to, where your tail is. So the tail is longer on the left. And something really interesting happens when we are skewed, when we're looking at skewed data. So the mean is typically less than the median, and I'll show you where that would fit on our curve in just a moment. So mean is typically less than the median. And one other thing here is the median is closer to Q3 than it is to Q1. So median is closer to Q3 than Q1, which is really interesting because the median is the exact middle point of our data, and Q3 is the exact 75% way through the data, and Q1 is exactly 25% of the way through our data. So if you're looking at the numbers in a list, they will be exactly the same distance from the median because you're looking at a very consistent, steady splitting into fourths. But when we put it in our curve like this, it changes because what actually happens is your median might be somewhere around here, which is closer to where Q3 will be. So this is your median. But your mode, which is the item that occurs most often in your data, is where the peak is up here. and your mean, which is going to be past the median, because it says the mean is typically less than the median, and that's going to be like somewhere over here. Like this might be your mean. And the reason why that happens is because this tail that's longer on the left, it's saying, yeah, most of your data is over there, but we're going to pull it this way because some of our data points over here are really strong and quite a bit lower. Now we're going to look at skewed right, which, like I said before, it's exactly the opposite. We saw that in our graph, and that changes with the mean, median, and mode as well. So our mean was closer to the tail, and it's going to be closer to the tail on this graph as well, so it's going to be further to the right than the median. So our mean would be maybe right about here, and our mode would still be at that peak because that's where most of our data is at, and that is what the mode is. It's the most frequently occurring data point. And then we also have our median, which is going to be closer to Q1 in this situation and further to the left than the mean. So our median, our middle data point, might be somewhere right around there. And to describe what's happening here, the tail is longer on the right as opposed to the left. Tail is longer on the right. And the mean is typically greater than the median. And the median is, again, closer to Q1 than Q3. And again, that's looking at the graph, not the data if it were listed out. So to zoom in on these two things, we have skewed right. We have a lot of data that's to the far end up here, and these big numbers are pulling our mean to the right. Skewed left, we have all these numbers over here that are really small, and they're pulling the mean to the left. So the median is always in the middle of your data set, but when you're looking at it on a curve like this, it might appear to be closer to Q1 because that's where most of our data is. But it is still in the middle. It's the mean that is affected by the skewing, and the mode isn't changed by that either. But the further you're skewed, the further your mean is going to pull. And same thing over here. The further you have your line over here, the further your mean is going to come this way. This is where we're going to stop for today. We'll pick back up with section 5 covering two-way tables.